Hello again, everyone. Jim Bayless. I'm going to try to do a few things here for you from chapters 16, 17, and 18 from the calc-based book, from the Katz book for Physics 209. But this also, very much of this can be applied to the non-calc treatment. If you're not looking at the derivations, having used calculus, let's say, to get to some of these derivations, just look at the actual end result of the derivation. That works for non-calc based classes and calc based classes as well. So hopefully that can be a pretty broad application for everybody. Trying to think of a good way to say some of this stuff and how we want to exactly approach it. I will say, let me try to summarize in at least halfway decent detail, chapters 16, 17, and 18. I probably won't hit every single aspect of what's in those chapters from the Katz book, but I think some of these highlights are very, very important, and they're going to help us with doing the problem. So it's a bit of an overview, as much of a summary, as much as it is a summary. It's a bit of an overview more than anything, but I think there's some good things we can talk about. When you want to talk about oscillations, you want to talk about anything, in fact, oscillations or anything else in physics, you try to get a mathematical representation of what's going on, if possible, or at least a very good approximation of a representation of what's going on. So when we talk about oscillations, there is the idea of periodicity. It's a periodic function. And later on, when we talk about stuff, well, I'm not really going to talk about it in this case, but I have in my notes they talk about the Fourier series and harmonic analysis in that regard, and how we can kind of take any periodic function and arrive at what it is, or very close to what it is, by superimposing a whole bunch of different functions that are much simpler. And the more of them we superimpose on one another, we can basically mimic any periodic function that we wish. So pretty interesting stuff. We're not going to go that far when we get to that point, but at least that's something you got to know. The book talks about it. At least know that it's out there. It can be done. It's harmonic analysis. We're not going that far, but we are going to say this much. We know it's out there. We know we can learn it. I've given you notes on the Fourier series, which is I hope a decent introduction to harmonic analysis if you ever get into that sort of endeavor, I guess you could say. Well, there's a lot that can be said, you guys, and I'll try to tie this all together. There is a handout I have on trigonometry and waves. I guess the trigonometry of waves, or sort of say the trigonometric representation, what goes on with waves. There is some really beautiful mathematics out there, as I always tell you guys, and our business is not so much being able to derive everything, but at least knowing it's out there and knowing that there are derivations out there. I try to give a lot of derivations, you guys, so it's at your convenience to be able to look at much of this. And again, there's just a tremendous amount of stuff out there, you guys, so at least we try to point to it. We know that from complex analysis, there's this beautiful mathematical formula where I is the square root of -1. E to the I theta equals cosine theta plus I sine theta. I think we've already touched on this elsewhere, and I definitely have it in my notes. A lot of this stuff is talked about. Much of it is derived, much of it we don't really have the time to derive it, even when we take more time on it, but at least we can point to where it is. There's derivations, or at least close to derivations, and some full-out derivations present, and other times we just point to what it is that we need to know when we're doing this. So e to the I theta equals cosine theta plus I sine theta. If you manipulate this, because if you go e to the negative I theta, it's cosine theta plus a negative I sine theta. So there's a lot of tricks of the trade out there, you guys. We can find out what the cosine of theta is. In terms of complex analysis. and get to here. We can find what the sine of theta is. That's I. That's square root of -1. Yeah, there's a lot there. So we have that. Let's see what else. With this in mind and using these trigonometric identities, we with substantial effort can arrive at the following identities and others. And it's going to be useful to us later, but for our purposes right now, I mean, there's a lot there, guys. There's a lot there. There's a lot of substantial effort we have to put into making this thing happen. We do what we can when we can, and other times we're going to take it on faith, what they're telling to us, and we can maybe leave it for some other time when we have more time to derive it. Usually that's a personal journey, but I do have a lot of stuff out there for you that is fully derived. Nobody's going to be able to derive everything in the time frame that they have, but there's a lot out there derived for you. You might want to look at it. So in Canvas. So with this right here, there's some identities they got, and they're used. There's a whole bunch of things. Alpha's an angle. All of these, I got to really mention, all these angles under consideration are radians. I don't want to get too far into this. You can make this work for any kind of degree measure that you have, whether it be revolutions, whether it be degrees. But for this to be as is, it is geared to the radian. The radian is the most natural degree measure that there is for all these formulas, including Taylor's formula later on. We're talking about some of the beautiful conclusions we can draw with Taylor's formula. When you're talking about degrees, the radian is the best way to go, is what they use. All of these are with radians. We can make stuff work if they give us other things. We're not going there right now. For right now, all of these would be in radians, how they're drawing these conclusions. Here as well. Radians, but you can make it, there's a lot, what do they say? Never say never, never say always kind of thing, guys. But let's talk. I mean, let's just, right now, let's assume radians and kind of make it a little simpler for us. And that's plus or minus cosine alpha sine beta. That's that one. The other one is cosine of alpha plus or minus beta is cosine alpha cosine beta minus plus sine beta. And they write a whole bunch of other stuff. So, I mean, this is true. You can write. Now, this is, I mean, like I said, we're going to leave it. You can, let me write it down, and maybe it's going to be easier to kind of look at how they get this. I can point to how they get this. To actually derive it would take a lot more work and a lot more time than what we have right now, but it is derivable. It does work. But let's see what we can say here, guys. Let me get better chalk, guys. Sine a half times cosine a half alpha minus plus beta. Okay, now we'll talk in a little bit about this, guys. If you had this, similar looks to this, I guess you could say, across the board. And this is in my notes as well, guys, if you don't get a good look at it, but hopefully you do. Okay, so there's a lot there. See if there's something else here I might be, and there's another one. It's hard to know exactly where you want to go when you want to start erasing some of this stuff, you guys. I wish I could leave all of it up here. I wish I had a whole bunch, a gigantic board to talk about. Then that becomes okay. All right, there's a lot here. Kind of tempted to put to say a few things here. Kind of put the carriage in front of the horse sometimes when we do this. These are identities. They are trigonometric identities. Typically, well, not typically, especially here, the thetas that you're using are radians. They are the measuring stick. They are the most natural way to measure angles. Here you can work in a number of ways, but the identities are arrived at through using trigonometric identities such as these, which only involve the radian, because the radian is the most natural measure of degrees. It's geared to the measuring stick of the distance on the number line from 0 to 1. That distance from 0 to 1 constructs everything. All our measuring systems that I've ever seen. I mean, and certainly hugely important measuring systems that are used throughout physics. That distance from 0 to 1 is a unit length of 1. From here, I can construct very big numbers, very small numbers, all the fractions. If I move that vector upward, I can get the i's, the square root of -1, and construct all the complex numbers. But the measuring stick is from 0 to 1. From that unit of measure, if I multiply that by -1, I point it the other direction and get all the negative numbers, etc., etc. That measuring stick, that length from 0 to 1, from there you can build every number that you wish to build. That measuring stick from 0 to 1 corresponds to how the radian is set up. The radian defined as a unit of length, as a unit of degree measure rather, not length. The radian defined as a unit of degree measure is scaled to that measuring stick 0 to 1, the same way all the regular numbers, non-degree numbers, so to speak, the way all numbers in the real number system are scaled to that measuring stick from 0 to 1, so is the radian. So you go with the radian. All these can be arrived at through manipulation of these realities that can be proved. How they get proved is some absolutely beautiful mathematics. How this stuff gets proved is absolutely beautiful mathematics. Not incredibly difficult, very tedious. Okay, we can point to it. This would lend itself more to an in-person discussion with people to talk about it. I could point them to various great books. by Fritz John and Robert Courant and Ivan Sokolnikov. Sokolnikov wrote some really classic books. They get into stuff like this. There's other. They don't. I've not really seen the proof the way that I most like it. But who am I to be saying anything, right? I'm just one man's opinion here, I guess. But there are ways I could tell you about this stuff that I think really lends itself to a decent common sense understanding. But it's very tedious. It's very tedious. And I'm certainly not the first person to have looked at the proof I'm thinking of in the way that I'm thinking of it. I'm sure it's been done before. I just haven't seen it in too many places. But very tedious, not incredibly difficult. The time just isn't there, you guys. But it's just some wonderful conclusions and discussions. Ivan Sokolnikov, in his book Advanced Calculus, 1939, does great work pertaining to these matters. No book is going to be exhaustive in the discussion of the mathematics that's out there. I'm certainly not able to be exhaustive regarding that, and I don't think anybody is, to be honest with you. But some wonderful stuff out there. It looks like this. What is so important about identities like this is waves can be described in terms of mathematics like this to a large degree. And there's stuff you can say about that and how exactly you want to say that. I'm just trying to argue with myself now how exactly I want to be going about it. Now, we said this right here, and I think we're going to remember this and come back to it. Well, this idea of trigonometry and waves and things of that nature, what can we say? Well, let's talk about oscillations and how they're described in wave motion, and there's a number of things can be said. Again, as I'm doing this, I'm debating with myself a little bit how to go with this, but let's leave this as is, and let's say, okay, well, all these functions oscillate, and in fact, I could create oscillatory behavior or behavior. We could describe oscillatory behavior by using trigonometric functions, using this stuff as our basis to get there. Again, the mathematics is wonderful that pertains to it. So if you're saying that, you could say, well, let me see what we're talking about. You could say that a number of things about this. So what we could do is let's kind of there's so many approaches to this, what you could do first, what you could do last. Let's just kind of talk a bit about it and see what we can do about it. We know that see a bunch of ways we could actually say this. We've talked about things in the past. Let's talk about this. Let's draw a circle. And let's put a mass at the end of it. Mass M doesn't have to necessarily be a mass, it could be a point. The radius here is R. Sometimes they write R, you can write it as R. You can also call R A for amplitude. This will become more clear in a bit. Let's see exactly how you want to maybe look at what's happening regarding this thing. There's different symbolism you can put here. We're not going to make the biggest deal in the world out of the symbolism that can be there, but let's say let me put a screen right here, I guess you could say, and let's shine a light. Let's shine a light from the far left hand from the far left hand side where I am. Let's shine a light here in a dark room or something. Let's shine a light here, and this is not composed of anything. It just shows the track that it's taking. It's standing vertical or it could be horizontal. That's not the big deal. The big deal is if you shine a light here, this shadow will move from the very top right here to the very bottom right here. And as this spins around, this thing will oscillate up and down if you're looking at the shadow of how it would move. Let's say, and there's many ways to go here, guys. I'll try to make it as easy as I can. Let's take the R and put it up here, and then later on, bam, it swings down here, but it's swinging all the way around. Okay. A is equal to R, as we said, right? And as it opens, at time t equals 0, it's right here. And then at a particular time, it opens here, theta degrees. And it's right here. So, where's the shadow? The shadow's right here. The shadow comes right here. Well, how high is the shadow? The shadow was up here. It ended up going down here. When you bring it all the way to here, the shadow will be here, and it'll just oscillate up and down. As this thing spins around, it's going to oscillate up and down. They call that simple harmonic motion according to how it works with a circle like this. It's a non-calc version way to look at some of this stuff. The very, very height of this thing, right here, we'll call this right here, we'll call it x equals 0. You could just as easily call it y equals 0, right? The trigonometry, you got to remember something about the sine function and the cosine function in general. The sine function and the cosine function are identical size and shape, if you allow me to say that. They're just out of phase with one another by 90 degrees, by pi over 2 radians. They're just out of phase one way or the other with one another. But if you pick up one, if you leave one of them graphed as it is and pick up the other one, and then you could pick up one of them and put it right on top of the other, and there's no difference in their size and shape. Their height, the whole thing. One falls right onto the other. It's hard to talk about a size when these things go on forever, but you know what I mean. For any particular period of time, any particular circumstance, you can put one right on top of the other. The cosine and sine function are basically identical in size and shape. Let me say that. And so it's a question of how you manipulate them to actually get an answer here. And this right here, down here, would be this guy, if he was here, right? And it'd be down here. And this thing oscillates back and forth. Well, this is x equals 0. Up here, this is x equals a. Why is that? Because that's the length of the radius, and you said that was a. Down here, x equals negative a. Let's see if that actually is going to work out okay for us. Can you tell me generally what's going on here? This will be a value of x, just a value of x right here. Well, how big is that x? How about it's as big as a cosine of theta? X will equal a cosine of theta. Interesting. There's a lot going on here. I'm giving you a non-calculus look at something like this, and we'll see what we're going to say related to it. And then remember some of the stuff that we said before this. Do you guys remember that we talked about the period? The period is the amount of time it takes to go all the way around. The amount of time that it takes to go all the way around is the period. So we know that that's 1 over the frequency. The frequency is 1 over the period. So these are both reciprocals of one another. We've seen those before. we know that omega is the angular speed. 2 pi radians in a circle get traversed in one period of time t. That's what omega is. If 1 over t is equal to f, the frequency, you can also write 2 pi over t is 2 pi f. So these are all one and the same, I guess you could say. So there's a lot we know. Well, true. I mean, we've said, that we've said a lot of stuff. Is it true? We could say a whole bunch of stuff, actually. How fast something's going and everything else. And if we're talking about centripetal force. You guys remember centripetal force was mv squared over r, or over a in this case. It doesn't really matter. And the acceleration is v squared over r. Remember that v, you guys remember that v was omega times r, based on things we've said in the past. If v is omega times r, v squared over r is m omega squared r squared over r, which is equal to m omega squared r. What's this? It's omega squared r squared over r is omega squared r. So on and so forth. All right, I mean, we've said this. So, we've gone along these lines, you guys. We remember this right here. Can we say some more? Yeah, remember we said that D was kind of like V times T. Theta is omega times T. So that's pretty important. That gets us, to a lot of some interesting conclusions. Theta equals omega times T. So I could just as easily right here say x equals a cosine omega t. How fast is omega? Well, depends what the angular speed is. We've been down this path before, guys. We were talking about the kinematic equations and how the kinematic equations are analogous to the rotational equations. Rotational kinematics or linear kinematics, the kinematic equations in a broad range of circumstances are completely analogous to each other. And we've talked about that. So we can go right here. We can say x is this. Well, yeah, I guess you could say that's true. Is there a speed at which this thing oscillates? Here's where it gets kind of interesting, you guys. This thing has a velocity right here. How fast that velocity? V. V is omega times r. Right here. V was equal to omega times r, or omega times a, because the r is the a, right? How I want to talk about it. I want to know, look, this is going v. This is going speed v, ladies and gentlemen. Always, like for our purposes. The v don't change. This thing's being whirled around like an old-fashioned slingshot. It's being whirled around. And yeah, v is going to be the same everywhere. Down here, v is going to be v. I mean, this is going to be v. Here, there's going to be a v. So on and so forth. Yeah, I get it. It's going at speed v. Is the shadow going at speed v? Only right here. Only right here, straight up here, and only right here, straight down here. The component of it. The component of the shadow, guys. The component of the shadow. Let's be careful here. This is V, the hypotenuse of a triangle I'm about to draw. Here's this. Here's that. There's a component this way that I'm not really counting, not really worried about. and there's a component this way. There's this way, and there's that way. This is the one I'm caring about. In other words, there's a component going this way, and there's a component that way. Well, wait a minute now. Let's see how good the math is. We got to be careful here. See, guys, I care about this component. This is the v sub x or the v sub y. It's the y component if y is up and down. Well, as luck would have it, for better or worse, I'm calling this up and down. I'm calling it the x projection, the projection in the x direction. If you don't like it, turn it sideways or turn it upside down, or take this guy and pick take this and pick it up that way. You can look at it that way. The big thing here, guys, is the mathematics. You notice this is the long one. That's the long one. That's V. Okay? And so let me, we just drew all that, all just to erase it, maybe make it look a little easier. But you've seen what the V is, guys. Okay, so if that's the case, let's stay with it. I mean, we got this, and we said, that's the V. There's this guy. Let me just draw more narrow. That might be easier for us to draw with. Okay, what is going on here? That's theta. That's 90 minus theta. That's theta. That's 90. Okay. Let's see who's who. Let's see what's going on here. Wait a minute. This whole thing is 180. This whole thing is 180. This whole thing is 180. If that's 90 and that's theta, this is 90 minus theta. 90 minus theta and 90 is 180 minus theta. This has got to be theta. Good. What is the projection then here? If this is V, ladies and gentlemen, this is V sine theta. That's V sine theta. So basically what we got here is, that's V sine theta. But what is V sine theta? Didn't we say that V was equal to omega times R? V is equal to omega times A. Didn't we say A and R were the same thing? V is omega A. V is equal to omega A. If V sine theta is this, V sine theta is, well, V is omega. Sine theta is this. Didn't we say that the sine of theta, didn't we say that theta, ladies and gentlemen, was omega t? Over there, way over there, we said that theta was equal to omega t. So it's omega A sine omega t. Regarding this, oh yeah, and by the way, it's going downward. It's a negative velocity. In this case, the negative. It's always opposite where it's going. So let's see here. So it went as it's firing its way down. That's the magnitude of it. So it becomes, for our purposes, the V. It's hard to say what the V is. We'll say the V sub x, the x component. No, what's x, what's y, right? I mean, we said this was x. This is the projection of x. So we'll call that x. I guess we'd call that y. Forgive me, guys, a little not used to what we're seeing. This would be nice to be seen as y. You could just as easily put a y in there. Just be careful. Just kind of be careful when you're doing it. You could put a y in there. It'd be the cosine. There's very many ways to write it. The big thing here is, how is this thing behaving? There's the A, but instead of a cosine, it's a sine. It's a sine. And the other one is, and then omega comes out as far as the magnitude. Why am I throwing a negative onto this thing? Because it's actually coming downward. It's actually coming downward. So there it is. I mean, it's doing some crazy stuff. It's flying downward, and it's actually speeding up as it's flying downward because it's going to go down like that. Just like over here, it's going to speed up as it comes up. So it's negative omega A sine omega t. Negative omega A sine omega t. Now, is there something else going on here that maybe I need to be looking at? Well, there's a disparity here. The acceleration here is not really a constant acceleration. I understand that the acceleration is a constant acceleration right here when you're talking about something in regard to the very outside of the circle. But in regard to how the shadow moves, the shadow comes to a dead stop up here. Comes to a dead stop up here. In fact, the theta here would be 0. If you put 0 right here, the sine of 0 is 0. It has no speed. Up here, it ain't going up and it ain't going down for just an instant. And then, bam, it starts accelerating downward. Its biggest acceleration, ladies and gentlemen, is going to be here and here when its velocity is the smallest. I understand it's going at velocity v in terms of magnitude in regard to that thing being whipped around the circle. It's not changing. It's going around at 100 meters per second. I get that. But how fast is the shadow moving when you put the light on it? When you put the light on this thing, the shadow moves differently. Here there's going to be highest height, but no speed. Lowest height, but no speed. Here, there's no height whatsoever, and here there's no height whatsoever, but it's going at its fastest right here. Why is that? It's a 90-degree angle right here. 90-degree angle, if theta is equal to omega t, if theta is 90 degrees, or pi over 2 radians, the sine of pi over 2, or the sine of 90 degrees, is 1. Negative omega A means negative omega times A. Didn't we say A was equal to R? So it's negative omega R. Wait a minute, omega R? Didn't we say V was equal to omega R? Which is omega A. So at that point where it's perpendicular to at that point where it's at these particular extremes, right at x equals 0, that's its greatest speed. At its greatest speed, there is no acceleration here. At its smallest speed, there's no acceleration at its greatest speed. Believe it or not. What are you talking about? Well, it reached that great big acceleration. It reached that great big speed. The shadow reached that great big speed because it got accelerated up to that point. But once it accelerates up to that point, that's it. It ain't going to accelerate anymore. Once it reached its highest place, its highest speed, there's no deceleration or acceleration for an instant. There's zero acceleration right here. There's zero acceleration right here, and there's zero acceleration right there. Here, at the highest speed, there's no acceleration, zero acceleration. At its highest speed, no acceleration. At its lowest speed is the greatest acceleration, is the greatest yank right back to get it. It's as simple as that. Now, how are you going to get acceleration of the shadow? How does that all play out? Well, there's a number of ways to look, guys. How is this thing accelerating? Well, I'll tell you what. I'm going to do. Is it true that there's an acceleration A sub c? There's acceleration A sub c going right in. Yeah, there is. That's everywhere. The centripetal acceleration is everywhere coming inside. I want to know what is the acceleration of the shadow. I'm always working with the shadow, you guys. You're going to see why I'm doing this in a bit. I want to know why the acceleration of the shadow works that way. Well, there's a component of acceleration this way. That doesn't really move the shadow. And there's a component of acceleration that way. That's the one I want. ACX. AX, ACX, AX. In the X, this is in the component of the ACX is just going to be AX. See how legible that is, guys, really quickly here. Not great, but okay, let me make sure you guys have it. So you got this guy right here. You got this, and you got this. You got the triangle. We're playing games of triangles again, guys. This right here is AC. Didn't we say, what did we say AC was, guys? AC was omega squared r squared over r. That's omega squared r. AC is omega squared r. AC is omega squared a, because the r and the a are the same. Yes? What is a sub x? And I'm sorry, the x's and y, I mean, this looks more like a y. I get it, but we entered the dance, we got to dance. Let's figure this thing out. Play trigonometry. If this is theta, and this is 90, this is 90 minus theta. Let's try it again. If this is theta, and this is 90, this is 90 minus theta. If this is 90 minus theta, and this is 90, this is theta. Okay. Corresponding angles are congruent. Parallel line, line, parallel. This line is parallel to that line, and this is the transversal. That's theta, that's theta. Okay. If that's theta, what's this guy right here? What do you say you take AC and multiply by the cosine of theta to get this projection? AC cosine of theta. Sounds good to me. AC is omega squared A. Again, guys, I can't emphasize it enough. I threw it past you pretty fast, but you saw this. You've seen this. You've seen this. You've already seen this. Omega squared A times, okay, let's see here. Well, omega squared A, that we said omega squared A is the AC. That was the AC. AC is this. Omega squared R, which is the same as omega squared A. Cosine of theta, cosine omega t. Now, I want you to kind of be careful. Right here, this guy's pointing downward, just like the velocity vector. Just like the velocity vector was pointing downward, so we said negative. The acceleration vector always goes in the same direction as the velocity vector. So you throw another negative on there. And that's that. Now let's write that down. Let's talk about it and see what we can say. There's a lot that's getting said, obviously. A lot getting said here, guys. So we said A cosine omega t. So let me not erase too much here. Let me actually write it over here and then erase it. Just so no careless mistake gets made, and I'm apologizing for signs being in the wrong place and stuff. So at the end of the day, x equals a for this. There's different ways to write this, you guys, but the basic look is what I'm giving you. X equals a cosine omega t. X equals a cosine omega t. V sub x equals negative omega a sine omega t. And a sub x is negative omega squared a cosine omega t. So there you go. You're looking at something like this. You say, okay, that's okay. This is the behavior of the shadow. This is the behavior of the shadow oscillating. This is the behavior of the shadow oscillating up and down. If I graphed mathematically the position of the shadow as it oscillates up and down with relation to time, it is describing simple harmonic motion. It is a simple harmonic function. It's cosines and sines. And if I graphed it, if I graph this one, for example, let's see what we could, you could see, it would start, for this one, it would start x like this, and then oscillate, and it would oscillate forever, let's say, looking like that. The sine function would have the exact same shape as this, but it have associated with the sine function, so it's moved over a little bit, and there's different constants right here in front. Omega and a are constants. If we were not dealing with the behavior of the shadow, if we didn't care about the behavior of the shadow, then we would be talking about this thing just whipping around. This thing whipping around, not concerning ourselves at all with what the shadow is doing, just concerning ourselves with the circular motion. Omega is a constant, V is a constant, and all the stuff we said earlier, mv squared over r is the centripetal force. V is a constant because omega is a constant and r is a constant. Not a big deal. But with the shadow, you guys, you've got to look at projections. Literally, it's like it's being projected on there, like it's a movie, right? The light that's here is projecting the shadow, and we're seeing how fast the shadow is moving. You don't have to use the shadow scenario. You can just say, well, how much is its projection in this vertical sense? Unfortunately, I called the vertical sense x. You can call it x, you can call it omega, you can call it y, you can call it alpha, you can call it beta. Who cares? But you're looking at how the projection behaves. And that over there that I have highlighted in green, circled, way over to your right, is the way you want to be looking at this. You say, okay, yeah, that's great. If you graph them, it is associated with a sine function. The cosine function is this thing called a sine function. The sine and cosine function are basically identical. They're just located, they're out of phase with one another. So oftentimes they call it a sine wave. The sine wave can actually be a cosine function, but it has the shape of the sine wave. The cosine and sine have the same shape. Okay? So this is how you would write it mathematically. In reality, you guys, there are actual waves that move like this, that oscillate up and down. And we'll get into that as soon as we can. If I can't do it in this particular discussion, we'll do it again. We'll make this, Oscillations and Waves 1 and go Oscillations and Waves some other one if we need to do that. Okay. So this is, something of interest, I think. Let's leave it there. This is called, what is going on here, the description going on here is called simple harmonic motion. SHM. Simple harmonic motion. And I can make, and let's say you want to draw a really bizarre looking wave. Hey, Malus, I got a wave to draw for you, man. You're like, look at that wave. Now you give me an equation to that wave. There are techniques where we can add all these simple waves together and get as close as we want to a really complicated wave, no matter what it is. As long as it's periodic, we can figure a way out. We can figure a way to do it. That's Fourier analysis. Okay, and I touch on that a little bit in some of the notes I gave to you guys. At least a little basics are given to you there. Okay. For our purpose, so they get into that and they mention that harmonic analysis using Fourier analysis. They use that they talk about that in chapter 18, but they don't go into it big time, and we're not going to go into it big time either. But again, it's out there. The Fourier series is beautiful. There's some real intuitive looks to it. Sokolnikov in his 1939 book, Advanced Calculus, does a great job talking about that. And I mentioned that in my notes as well. All right. Okay, we have all this. What's the point? Well, we didn't even talk about, not really too much advanced mathematics was talked about to actually do this. Not much at all. But we could get a little more complicated if you want and still draw the same conclusions. What's going on here? Well, I'll tell you what I'm going to do. What do you say? One of them is easy enough, I think. This x you said, this x is a cosine omega t. Yeah, and then they got this other thing, this v sub x, hey, it looks just like that guy, which is equal to dx dt. The time derivative of the x function will tell me what v sub x is. And that's more for the 209 guys right now. Those of you who aren't in the calc-based class and still have this background, that's good for your enrichment. If not, just draw the conclusion I'm drawing down here. dx dt, huh? A is a constant, omega is a constant. The derivative of this with respect to t, the derivative of the cosine function is negative sine function. And the derivative of the cosine function is negative sine omega t times by the product rule, the derivative of omega t. So in other words, give me the derivative of cosine omega t with respect to omega t, which is negative sine omega t. Then by the chain rule, do the time derivative of omega t, which is omega. So the derivative here is negative sine omega t times negative omega. I'm sorry, it's negative sine omega t times omega. Negative sine omega t times omega. So it's negative omega a sine omega t. Take the time, guys, forgive the speech I gave. Take the time derivative of this using the chain rule, you get down to here. A sub x is going to be dvx dt. It's going to be the second derivative of this. The derivative of the sine function is cosine. The derivative of omega t is omega. So the negative omega stays. You put another omega there. And that's what's going on here. You can do this in either one of my classes. Calc-based or non-calc-based. You can do it either way you want, guys. And here it is. You got this, you got this, you got that. And it's coming out right to here. Same thing I got here. So there's a lot going on there. Well, here's the crazy thing. I started this whole game playing with a circle and not using any calculus and just using the vertical projections of velocity and acceleration to find the velocity and acceleration of the shadow. And I used x for the vertical. Okay. You could just as easily be using y's. You could start this thing anywhere. In fact, you could do a lot of the mathematics. You could have made this with a sine function here. But then when you take the derivative of the sine function, you get the cosine function. When you get the derivative of the cosine function, you get the opposite of the sine function. So it's going to look initially different. It is the same mathematics, ladies and gentlemen. I said cosine, I can make all cosines look like sines if I do it right, if I'm careful. I can do all cosines and make them look like sines. I can do all sines and make them look like cosines. But this is the general, so you're going to see this differently written in different books. They might have the light on the bottom. Other places they got the light on the bottom. You want to see how this thing goes. It's the same thing. You can read their argument that way, specific to that particular context in which they're claiming things are valid, and they are valid. Use their particular argument in that particular context, and it's the same argument I'm delivering here. The functions look different. In substance, however, the mathematics is pointing to the same reality, okay? Because of the similarity of the cosine and sine functions. Okay. So that's pretty fascinating stuff. I mean, I guess there's big story there's bigger stories than that, I guess you could say. And we talked about it, and I gave and I have in my notes pertaining to oscillations. In my notes pertaining to oscillations that I have in Canvas, I also do one where I have a spring. And the spring oscillates up and down. And they got here, did I use an X? I used an X again, didn't I? Okay. You can use an X oscillating up. You can use the X as the projection in the vertical. You could just easily use a Y. Let me use an X, but let me use it in a little easier sense when we're talking about some of this stuff. The real hard part here, guys, is it's hard. It's generally hard. I'll do very similar to what I have in my notes. I'll just do a little more of a simplified version of it. Remember all this. You can always go back, and I'm always kind of forgetting that when I'm lecturing. I think I'm like it's live, and we can't really put the tape back at all, but you can put the tape back and look at it. So we got this. Look at it. You're about to see the exact same thing, or very, very close to it. Okay, that in substance it's the same thing. Okay, so with that in mind, let me try to see where I want to go. I'll just erase one of these and I'll leave that one up there. And remember this circle. You're thinking, what is he about to do here? He's about to do this with a spring, and yet it's going to have equations identical to what was going on with the shadow of the mass that was going around the circle. There was a shadow moving around, and it mimics, the motion is mimicked, the motion we're about to see with a spring, a mass attached to a spring, is going to essentially exactly mimic what was done with the circle. Well, there's a crazy thing here, man. They end up saying, and let me just make sure, guys, we're okay. With this spring up, but this only works for the spring I'm about to put in here, you guys. Let me try to think about it. Yeah, I think it comes out to this. Omega is the angular speed. Yeah, K is the spring constant, M is the mass that I put at the end of it. For what I'm going to show you, the omega you'd put in here would be the square root of the ratio K over M. Is that always the case? No, but it is always the case when there's a spring constant, a spring with constant K, and a mass of mass M. Yeah, then it is. Otherwise, there's other ways the equation gets solved for. But this omega, I put that there and put the carriage in front of the horse again here. And let's see what we can say here. Let's say there's a spring. It's not going to be, we don't got to be real fancy, guys. We just got to kind of see where we're going here. Here is the spring. Here is the mass M. The spring is an ideal spring. If you compress it, it pushes back as hard for X meters of compression as it would pull for X meters of stretch. If you stretch it 10, this could be a huge spring. This could be a spring that's, I don't know, 400 meters long. Maybe I'm stretching this. Maybe I could take this spring. It's an ideal spring. It's just relaxed. If I stretch it 100 meters, if I take the mass and stretch the spring 100 meters, it's going to want to pull back and restore to where it was. If I take it to where it was and then compress it also 100 meters, it's going to want to push toward where it was. So always it's trying to push back to where it was. At a 100-meter stretch, it may be pulling with 10,000 newtons. At a 100-meter stretch, it may be pushing. I may stretch this thing out to here, let's say. Trying to think what to use, guys. 100-meter stretch, it wants to pull in with 4,000 newtons. Now, let's say it wants to pull in with 500,000 newtons or whatever. 500,000 newtons if I stretch it 100 meters. If I compress it 100 meters, it also is going 500,000 newtons the other way. If I stretch it X meters, it is pulling 100,000 meters, 100,000 newtons of force of pull if I stretch it 100 meters. If I compress it 100 meters, it is also the same magnitude force, 100,000 newtons, but now it's push. If you stretch it X, it's going to pull with F. If you compress it X, it's also going to be F, but it's going to be pushing with F. So an ideal spring does that. So we got this, and we got this. And this right here is the amplitude. This distance right here is amplitude A. This distance right here is amplitude A. This is called x equals 0. This is x equals A. This equals negative A. If this is pushing this way, if this is pushing this way with 100,000 newtons, because you compressed it 100 meters. This will also be 100,000 newtons of force, but it will be a pull because you stretched it 100 meters. So it's symmetric. It behaves the same way in terms of magnitude of force, whether you compress it or stretch it. Ideal spring. So if that's the case, I'd like to see how this thing behaves. It's going to have its slowest speeds at the outskirts. It won't go further than when you stretched it. If you stretched it 100 meters, it ain't going to go further than that when it bounces back. Let's say it's on a frictionless surface. It's on a frictionless surface, so this thing will oscillate forever until it hits something or something hits it. It'll perfectly store the energy. The spring doesn't get weak, no dissipation due to friction or anything like that. So if that's the case, none of that stuff right there. It's a frictionless surface, and here it goes. It's going to oscillate back and forth. When we do that, is there anything you can say? Well, I already kind of put the carriage in front of the horse. I told you, remember that. Let's see what we can say. Is it true that the behavior of this, the mass M, right? Mass M, you guys. So, never know how good this stuff, how it looks for us. Okay, so it's mass M. Can we say this? Force equals mass times acceleration. True. Force equals negative kx. I got to put the negative in here. It wants to restore. It wants to restore what's going on. And it's a vector. It's got to be a vector. So in other words, if you stretched it in the positive direction, the force MA is negative because it tries to go back to where it started in the negative direction. If you compress it in the negative direction, negative times negative gives you a positive. It tries to restore in the positive direction. So I want you to look at this. I want you to look at that very carefully. MA equals negative kx. Okay, good enough. Acceleration, you guys saw me do it last time. It's dv dt, but it's also d squared x dt squared. Now here's where the calculus version comes in for the 209 people. The guys in the 120, if you got the calculus background, you want to look at this, great. If not, just be aware of the conclusions. Be aware of the conclusions that they're drawing here, guys, and you should be okay. I've got this right here. All right, add a positive kx on each side. Write it like this. I got to make something really clear to you guys. Make something really, really clear to you guys. That's a differential equation. It can be solved in a number of ways, and there are a lot of different things that happen. Here's what I mean. Guys, you saw me take the mass here. Take the mass here, and then it oscillates back and forth, right? Right here, right? It's going to oscillate back and forth, right? We're doing that, yeah. You could also use this mathematics, in essence. You can use this mathematics, ladies and gentlemen. You can use this mathematics if it was a pendulum, as long as the pendulum's not taking a real big angle. If it's a pendulum, it behaves very much like a spring. A pendulum always wants to restore where it's going. It keeps going back and forth. If it's a simple pendulum and there ain't a big angle involved, this mathematics comes into play. If you've got something that you can twist and torque, twist it, let it go, and it oscillates back and forth, that's called a torsion pendulum. I already told you the simple pendulum, and it works with this equation with the simple pendulum. It works with this equation with the simple pendulum, and it also works with the spring system that I just proposed. So for the springs it works, for the simple pendulum it works. For the torsion pendulum, I can show you mathematics where it works. And if there's like a bulky object and you hang it somewhere associated away from its center of mass, and you just let it go back and forth. You know, and let's say there's a huge, a huge piece of steel, and you put something through the steel, and it's not right through the geometric center of the steel or center of gravity or anything, but just somewhere there, and you just let it go back and forth. You oscillate it back and forth. So it works. That's called a physical pendulum. So it works. All of this works with physical pendulums, torsion pendulums, simple pendulums, small angles. All these are small angles. Typically, they're looking at small angles. Want to do this. Typically, you're looking at reasonable angles, small angles. It works for a physical pendulum, a torsion pendulum, a simple pendulum, and for a spring. For springs, simple pendulums, torsion pendulums, and physical pendulums. This mathematics works. And that's great. How are you going to do it now? Well, there's a lot you can do. Do you agree you can take do you agree you could take here and divide by m all the way across? Now, you don't have to know this stuff, guys. I want to say, okay, that k over m is kind of staring me in the face because I jumped the gun earlier and I said square root of k over m. So maybe there's a connection here. Okay. Right here, you get right here. I want to make this very clear, guys. I can make equations not verbatim, letter for letter, the same as this equation, but I can make equations that are essentially mathematically identical to this equation. And I can do it for the simple pendulum, the torsion pendulum, and the physical pendulum. In addition to the fact that I'm doing it for a spring. I can do it for all of those, and all this mathematics holds. They may not look, the symbols may not look the same, but the mathematics is identical. The mathematics essentially is identical. And I have that on Canvas for you guys if you ever want to look at it. I mean, I have that. It's there for you if you want it. Do you have to go derive all that stuff to get through these exams? No, not really. But it's there for your personal enrichment if you want to go that route. Okay. You go to here. What they do here is, and I'm not going to blow this up too much, guys, but our guess is that the solution is going to be of the form. The solution, we guess our solution is going to be something of the form C is a constant, e to the RT, where R is something. Since C is a constant, we will initially not worry about it. Afterwards, we consider it. They take this thing right here and they use differential operators. I'm not going to, if you're going to say I'm not explaining this to you very well, you'd be right. I don't want to explain it. I just want to say, for those that got the background, if you ever take differential equations, they throw something like this at you. And this is where d is equal to d dt. Our guess is that the solution is going to be something along these lines. We'll worry about what c is later. X is going to be somewhere along those lines. So let's say x is equal to e to the RT. The exponential function can get you out of so many things, you guys. We can talk about trigonometry using the exponential function, and we can also solve numerous equations because of the unique behavior of the exponential function when it's base e. E to the x is a fascinating function. The exponential function, in the argument of a famous mathematician, I think his name was Walter Rudin, had said it's probably the most important function in all of mathematics. It occurs in many, many places. It behaves in a fascinating manner because the number e behaves in a fascinating manner. That's a topic you could make a whole course out of that. That's a topic of another discussion, how it behaves. But x equals e to the RT is what I'm guessing the answer is going to be. Can we talk a little bit regarding this thing? If that's the case, don't want to erase any of it, but I'm going to have to, guys. Let me get out of here. You see this. Let me erase it. I'm going to have to erase it. I don't want to erase it, but I have to erase it. What is going on here? They're making the claim it works. Yeah, let's see. X equals e to the RT. We say a whole bunch of jazz way over there to your far right. So we're saying x equals c is a constant, e to the RT. Since it's a constant, we're not going to worry about it too much. Let's just stay right here for now, and let's see what we can say. Ladies and gentlemen, if you do this, what's the second? What is fast? I already said it. I already delivered that speech, and I can't even, there's no way I'll ever do it justice. The exponential function is fascinating because of the behavior of the exponential function, and that's largely, if not entirely, that's very largely due to the behavior of E. E itself. There's so much you can derive with that number E. Where E is equal to, E is equal to 1 over 0 factorial, which is 1, plus 1 over 1 factorial, plus 1 over 2 factorial, plus 1 over 3 factorial, plus 1 over 4 factorial, believe it or not, plus ... forever. Well, it goes forever, but it sums. It sums to 2.71828. Let me just... I got to here, guys. I didn't want to go there, but I did go there. Yeah, 2.718281828. but it goes forever. And that's approximately equal to. E is approximately equal to 2.7 1828. Kind of interesting. It goes a lot more. I mean, it goes forever. It goes forever. It's an irrational number, you guys, but this is approximately what it's equal to. 2.7, 1828. Something approximately. This goes on forever, but it does converge. The behavior of that number is absolutely fascinating, and it explains very, very many things. One huge reason, if not the reason, but I'd have to look more closely at it, but certainly a huge reason for why the exponential function is so important. E behaves, the number E behaves as it does, and it's fascinating what the applications are. To a large extent, the fascinating behavior of the number E when it is manipulated, used, explains a tremendous amount. So when Walter Rudin was saying it's the most important function in all of mathematics, yeah, the number E plays the huge role in that being the case. Arguably plays the huge role for that being the case. All right. We have it here, guys. You look at it. So what? What is there? Are we seeing something here? Can we say something here? The second derivative with respect to time, we already said the exponential function behaves in a fascinating way. The first derivative here is r e to the rt. The second derivative is r squared e to the rt. That don't look a heck of a lot different than e to the rt. Again, it's a fascinating function. I'm going back and forth thinking to myself, what makes it so fascinating? There's a lot of things that make it there. We can point to a lot of things. Its behavior is fascinating. Okay, so what? What's the big deal? What the big deal is, if this right here, now let's I gotta be careful. I'm gonna probably get over there a little bit. If d squared x dt squared is r squared e to the rt, and this is k over m e to the rt equals 0, look at it. Look at it carefully. So we'll put the C there. It's hard to explain, guys. Forgive me for going back and forth as to how to explain some of these. Why a function's fascinating. It almost gets to the level of a philosophical question. Pretty fascinating stuff. Beautiful stuff. Big time. Here's e to the rt. Here's e to the rt. It's good enough for me. That's always a positive number. This is never equal to 0. So divide by e to the rt on each side. Really? Okay. I guess I'm trying to find r, you guys. I mean, the big thing was we're looking at these guys kind of running the show. We're looking at these guys running the show. May I ask you a question? Is r plus I, which is the square root of -1, times the square root of, here's the square root of k over m. Last but not least. Okay, here we go. Here we go. We got to talk. We got to talk. We got to be careful. Is r times r squared? Is I times negative I 1? Is the square root of the ratio k over m times the square root of the same ratio k over m equal just k over m times 1? Okay, true. Is this positive ri square root of km, positive ri square root of km, and this is negative ri square root of km? Forgive me. This right here, r times I square root of k over m, r times I square root of k over m, and this is negative r times I square root of k over m, that's 0. And the r times r was the r squared. The I times negative I is 1. Square root of this ratio times square root of the same ratio is just the ratio. Bam! That answers the question. What are the answers? You got to set it equal to 0, so r could be equal to, ladies and gentlemen, r could be equal to negative I square root of k over m. Or r could be equal to, that's negative I, or I. Yeah. R could be negative I square root of k over m, or r could be positive I square root of k over m. Okay, without further ado, mathematicians make up stuff all the time. You can say whatever you want. What do you say you call square root of k over m? Right now, let me just call it omega. You may not be comfortable with it at first glance. Don't worry about it. Call it another letter if you want. Call it alpha. Alpha equals square root of k over m. Call it, I don't know, call it something else. Call it gamma. Lowercase gamma equals the square root of the ratio k over m. But I tell you what, that's not going to, why should it be an issue? I can call it whatever you want. Call it omega. If you call it omega, guys, then the answer, e to the RT, is e to the negative I omega t, or positive I omega t. Wait a minute. Didn't we say that e to the I theta is cosine theta plus I sine theta? And the theta is this. Here, it's cosine omega t plus a negative I sine omega t. Okay, guys. What's going on here? By hook or crook, we took the exponential function and we got to trigonometry. By hook or crook, we took the exponential function and we got to trigonometry. Either the cosine or the sine solves it. You can say, wait a minute, you got two things there. You got a real thing, you got something real, and you have something imaginary. Is that the whole solution? Yes. And the short answer, yes. All the real parts solve the differential equation. If you put the sine function in here, the second derivative of the sine function, derivative of the sine function is cosine. Then the derivative of the cosine is negative sine. Here's negative sine, here's positive sine. They add up to 0 if you play your cards right. Didn't I say if x was equal to the sine function, the first derivative of the sine function is cosine, second derivative, then the derivative of the cosine function, was the second derivative of all of this, is negative sine. Negative sine and positive sine is 0. You want to put cosine in there? Be my guest. Derivative of cosine is negative sine. Derivative of negative sine is negative cosine. Negative cosine, and put the cosine right here. Cosine and negative cosine is still 0. Either one of them will solve it. Wait a minute. Either one will work. A lot of times they just opt for one or the other. Sometimes you got to put both. In this instance, you don't. You could use either the sine function or the cosine function, but you got to be careful how you do the boundary conditions. I don't want to make this into a math class, guys. I don't want to make it more into a math class than what I sometimes do anyway. You know, I think it's important to make it into a math class at some level, but I don't want to completely go there. There's so much here. As I said, I cannot tell you, this stuff is beautiful. The way the exponential function behaves, the way E behaves, it really warrants your attention. If you're going to get serious about mathematics, get serious about physics. All that's neither here nor there. The answer is going to be the sine function, or it's going to be the cosine function. And that's where they're getting all this. That's where they're getting all this. And like I said, let me just see how I, just remind myself how I did it. I think it's got a little more detail here. In short, either cosine or sine, either cosine or sine function solves this because they are essentially the same function, only that each one is out of phase with the other. That is all the difference that there is. Both the real and imaginary parts solve the differential equation, and I get into it. And then I went into, okay, here it is. Yeah, here in the same thing. There is the simple pendulum where it gets talked about. There is, and I go into it in I hope, quite decent detail. There's the physical pendulum, the bulky pendulum, as we said. So there was the simple pendulum with a point mass at the end. Then there's the physical pendulum. Then we have the torsion pendulum at the end of all that. And Dr. Katz discusses this very well. We have the torsion pendulum as well. And let me just see here. Right. And then it's all here, guys. It's all in here. Look at it. You don't need to be the expert at deriving why this stuff is true. But I promise you, if you look at the physical pendulum that I've talked about, if you look at the physical pendulum that I've talked about, if you look at the torsion pendulum that I've talked about, and if you look at the simple pendulum that I talk about, they look like this spring. The mathematics resembles the spring. It's going to be different names, I guess, of items being there, but the mathematics is identical. Mathematics is identical. So look at it. It's your call on that, and I also go into other details regarding damped harmonic oscillation and things of that nature. Okay. I think that's about it. I mean, there's some more I was going to say. I'm sort of debating where to start, where to begin on some of this stuff when we actually do it. But there's some other stuff I'm going to talk about as well and bring forward. For right now, I think I'm going to leave it at this, and then I'll probably, I'll just call this one. This will be the part one of Oscillations and Waves, and then part two should get us largely through it. Okay. All right. Thank you very much for your time, you guys. Take care.